Dear colleagues, good morning, good afternoon, good evening. Welcome to this technical breakout session on DC protection systems from the promotion project. My name is Dirk van Hertem. I'm an associate professor at the University of Leuven in Belgium, and I had the honor and the pleasure to be the coordinator of work package 4 within the promotion project, which is called DC grid protection. Now, DC grid protection, it's actually something new. It's a new problem that we dealt with within the project. Now the question is that really true? Is it different? How does it differ from traditional AC protection? And it's very important to recognize that in a DC system, in case you have a fault, the behavior of that fault current, or the fault itself, is completely different than what happens in an AC system. So what happens is that you will have a very fast rate of rise of the current. The steady state value is much higher, as the DC value is not limited by the inductance of the lines. And at the same time, you don't have any zero crossings of the current, which makes it very hard to actually interrupt a DC fault. So the arcing behavior is dominant in the braking action only, right? So, and at the same time, we deal with a system which makes use of power electronic converters, which are very sensitive to overcurrents and which are at the same time also rather expensive equipment. So it is a different kind of animal. We need to be fast, we need to be more careful in our DC grid protection than we would have been in an AC system. So the main thing that we would like to investigate within this project, or this part of the project, is DC grid protection technically feasible? So how to detect the faults, how to ensure selectivity, which strategy to use, what is the effect on equipment requirements, and how do you actually compare and test or validate the protection system? How can we actually know that it is good enough? And that meant that we had to go into a risk-based assessment of the protection systems. The second big question was, is the equipment ready? Can we develop the necessary prototypes? We didn't talk about the DC circuit breakers because you might know these are different work packages from the promotion project. We focused on the secondary equipment and more importantly on the IED. And once we had these devices, we also needed to be sure that we could validate that. Throughout the project, we tried to go beyond the academic research and provide the evidence that DC grid protection is ready for the market and interoperable. To do that, we also had to look at the cost. DC circuit breakers are more expensive than AC circuit breakers. The setup of a DC protection system was likely going to be substantially more expensive than an AC protection system. So the question was, okay, is this protection system really blocking the development of the DC grid? Is that going to be too expensive? Maybe it's technically possible, but we cannot actually. Of course, this work is not done by one or two persons. There's a big group of people behind that. And on the right-hand side, you can see the symbols or the logos of the different universities, companies, vendors, TSOs, and consultants involved in these tasks. Formally, the objectives of the work package 4 of the promotion project were the following. So we wanted to have an industry-ready DC grid protection development. We wanted to develop a set of functional requirements for various DC grids, from small scale to large overlay grids, and for a variety of system configurations and converter topologies. We didn't want to have a system that worked on one particular grid, but we need to be generic. To analyze a wide range of DC protection philosophies on a common set of metrics. So really have to know why we make the different choices. We wanted to identify the best performing methods for the systems under study and to develop detailed protection methodologies for those selected methods. We wanted to develop a configurable multi-purpose HVDC protection IED to enable the testing of the different methodologies. And we wanted to investigate the key influencing parameters of protection systems on the cost-benefit analysis. In practice, this was organized as follows in different work packages, which took information from the earlier work packages and then afterward provided them to For instance, we're package 9 on the DC grid, DC grid protection demonstration, and we're package 12 on the DC grid roadmap, for which you will definitely hear more within the other breakout sessions or in the final conference. So rest me today as a last part of the introduction is to quickly guide you through how we're going to tackle the session of today. So of course, we started with the introduction and the objectives from myself. The next presentation will be given by Kamran Sharif Abadi from Equinor. He will discuss the functional specs of DC grid protection. Afterwards, we'll talk about the basics of DC grid protection, the algorithm and the protection strategies, the failure modes, and the KPIs of DC grid protection. Next, Ilkayan will present the open source promotion HVDC relay. Then we have a set of 5 more detailed presentations, because next to the high-level discussion that we had, we also had to go into the technical details. So we talked about the converter breaker protection strategy is newly developed within this project, the full bridge converter protection strategy, which was refined and let's say made practical, the post-fault pole rebalancing, the multi-vendor HVDC protection, and the backup protection. And we end with the CBA, the cost-benefit analysis of HVDC grid protection, with 3 different contributions on that topic. And we end with a short conclusions and key takeaways. Now, it rests me to say that I hope that you enjoy these technical presentations the next 2 hours, and I look forward to receiving your feedback on this matter. Thank you very much.